Welcome to Lecture 17A, two lectures in the Lecture 17 series. This lecture is entitled Line Integrals of Vector Dot Products, Definitions and Interpretation. So this is more or less background work into some of the issues that we'll be dealing with in the next couple of lectures. So the material here can be found in Reading Assignment 4, under Introduction to Reading Assignment 4 and sections 1.2 through 1.4. And the objectives of this particular lecture is to basically understand the importance of geometry and developing intuition, the graphing of vector fields, introducing you to new definitions, and integration of what we call contour integrals, which will be useful later on when we start looking at some actual physical problems in which vector calculus relationships are exploited. So the concepts and visualization skills are quite lengthy, but we'll go through each one of these in turn. And so just a reminder that this lecture introduces you to new material and is quite dense, so it is advised that you read the relevance parts of Reading Assignment 4 in parallel. All right, as usual, I'll skip this slide. This is just an overview of the slides to follow. Okay, so that's just a little bit of a background regarding how this material relates to the organization of material in Reading Assignment 4. And so what you'll find is that the contents of Reading Assignment 4 directory contain these documents. So there's the main document, which is the introduction to the divergence theorem and Stokes theorem. And we'll go through parts of it now and then move on to Reading Assignment 5 and then come back to it later. But that's just some information for your use. And then there are 4 appendices. These are not must reading. They're useful to look at in future, but I'm not going to expect you to look at them, but by all means, if you want to, you can. And also there will be the solutions to Reading Assignment 4. So there are a number of problems embedded within Reading Assignment 4, and if you want the solutions, you'll find them here. All right, now some of this material also appears in Chapter 17 of the textbook, but we're not going to be using it because Chapter 17 of the textbook took a different philosophy in terms of ordering a material. And so if you were to try and read that, you'll probably get very confused. All right, so the part of this lecture that we'll be interested in is, in fact, the first part of Reading Assignment 4. And so the topics are just a general overview. The teaching pedagogy, which I will not talk about now, but in the next lecture. Similarly, a geometric approach and the process of discovery. Probably focus more on this in the next lecture, but allude to it in this lecture. Graphing of vector fields. This is more or less a continuation of Lecture 1 in terms of here we add a little bit more body to the topic. And then I'll introduce you to the various definitions, which will be very useful basically to remember as we move through the remainder of the course. And then the derivation of a contour integral from a Riemann sum and examples. So this is more or less what's going to be covered over the next two lectures or so. All right, so let's look at geometry here in particular. And I'm looking at what I call the tangent normal vectors on open contours in 2D. We'll extend this basically to 3D as well. So if you look at the diagram on your far left, right, this is just a diagram of a line going between 2 points, a curved line. And then we can define a tangent vector at each point along that line. And we're going to define it as capital T ds. ds is a differential arc length. And t is a unit vector that points in a particular direction tangent to the contour at a given point on the contour. You can extend that to the 3D case, an open contour, of course, here meaning that the 2 points do not connect back to each other. And so in this case, it would be a 3D picture rather than a 2D picture. And then the third case is a normal vector in 2D, and I'm showing basically an arrow which is perpendicular to a tangent vector, tangent to the contour. And that's just n subscript s ds, ds again being the differential arc length. So I've just summarized here very quickly, the different notations. A unit vector tangent, a unit vector normal, and ds is a differential arc length. Note, the unit tangent vector t and unit normal vector ns can have two possible orientations. So for instance, you can have the tangent vector basically moving from bottom to top, or from top to bottom. And similarly, the normal vector can be pointing up or can be pointing down. So that basically produces an ambiguity, but usually the problem will specify which orientation to consider, or the orientation is decided by convention. So let's carry on. Let's take, again, the geometrical approach, but in this case, we'll be looking at tangent vectors on closed contours in 2D and 3D. So here, for instance, we want to make a distinction between two types of contours. One contour which is discontinuous, and one contour which is continuous in terms of the contour. So if you look here, there are four discrete segments here that make up this closed contour. We cannot describe this basically by a single tangent vector. Why? Because this line is not continuously differentiable. So we would have to basically look at this as four separate problems. Here, on the other hand, is a smooth contour, and so this can be represented by one tangent vector, as shown here. If we look at, if we now consider, for instance, 3D, so that'd be 2D case. If you look at 3D, here is just an example. Again, this is a discontinuous case, and this would be a continuous case, where basically you can represent a tangent vector for every point on this contour around this closed contour. And again, t is a unit vector tangent to the contour, and ds is a differential arc length. Again, just to make a note that the unit tangent vector t and normal vector ns can have two possible orientations, but usually the problem will specify which orientation to consider, or the orientation is decided by convention. That convention, more or less, is the right-handed convention. All right, so one little additional note here, that a normal vector ns in 3D is not considered. You'll notice that I only basically considered, in this particular problem, only tangent vectors. The reason being that if you try and fit a normal vector to a line in 3D, there are an infinite number of choices to consider. That means that there's a lot of ambiguity, and so anytime math has ambiguity, we tend to sort of walk away from it, and so it's not very useful to consider. All right, so on the other hand, if we're looking at the normal vector in itself, not the tangent vector, then in 2D there are no issues. And so again, the issue of discontinuous versus continuous comes up. So you'll notice here, for instance, there's just four discrete segments. This contour is not continuously differentiable, so we're going to have four different sections to represent this closed contour. And this represents a continuous contour. In this case, you can represent this closed contour by a single normal vector. And as usual, the definitions for ns apply. If we move to 3 dimensions, though, we now basically are able to make some sense of a normal vector. But in this case, the normal vector is normal to a surface. So for closed surface. So for example, here, you'll notice I've got a closed surface representing 6 surfaces. It's just a rectangular box. So again, we're not able to define one single normal vector for this whole closed surface because the surface basically here has an edge, and so this is not continuously differentiable. On the other hand, if we take something like a sphere, which is smooth, then we can represent this by a single normal vector to represent each point on this closed surface. So this is the case when we're dealing with normal vectors for 2D over here and for 3D over here. And again, we have the definitions here, ns. Now the distinction now is made between a lowercase subscript s and uppercase subscript capital S. Little s will mean arc length, capital S will mean surface. So just make a note of that. Generally speaking, I'll try to stick to that convention. Again, we have the problem here that this could be pointing outwards or pointing inwards, because in both cases, the vector is going to be perpendicular to the contour at a given point. And so usually the problem either specifies orientation or it's decided by convention. Similarly here, for instance, the arrow can be pointing out from a surface or inwards from the surface. So same issue will apply here. Anyway, so that's more or less just a sort of a brief overview of some of the conventions. and also basically how to look at this from a geometric standpoint. All right, so now let's do a little discussion on graphing vector fields. I'm choosing here a 2D vector field because it's easier to graph. It gets quite messy when you're trying to graph 3D vector fields, but by all means, you can certainly do it. It's just a little bit, you've got to keep track of where you put the vectors, vector arrows, and how long you make them. So there's a more detailed discussion of the graphing vectors in section 1.3 of Reading Assignment 4. So we're going to just take an example. Let's take the vector field f to be minus yx. And so how are we supposed to graph this? So the simplest thing to do is to create a little table. And so what I've shown here basically are 4 different positions corresponding to these blue bars that you see here. So minus 1, 0 would represent this position. 0, 1 would represent this position. 1, 0 this one, and 0, minus 1. So at this position, for instance, here, what we need to do is to plug in these values into this to describe what the vector looks like at that point. So if you put minus 1 into here, then the minus 1 will go here, and the 0 will go here. So that means we expect the arrow to be pointing downwards at this location, which is what we see here. Now you can do this for all the other remaining cases, and what you'll find is that the arrow points downwards here, to the right here, up here, and to the left here. Now, if you do this for different values of x and y, let's say you make this instead of minus 1, 2, so just put 2's in here. And as you move outwards, the magnitude of the vector gets larger. And so if you'll notice here, for instance, the arrow starting here is small, but if you move outwards, the arrows get longer and longer. So effectively, the length basically is changing as a function of position, and the direction is changing as a function of position. So this is a very simple way to take an arbitrary vector field and graph or sketch it out in this fashion. The other thing would bring your attention is the definition of what we call a radial field. We'll make reference to this frequently. So here we're saying p is a real number and k is a constant. So in 2 dimensions, right, if you have a vector field that's x and y, right, then r is a vector which has got an x and y component. This is the magnitude of the vector r to some exponent p times some constant k. This can be basically written in unit vector form by taking this out, which is r, dividing by the magnitude of r. That means that you're left with r to the power p minus 1. Okay, so this is the unit vector which gives direction, and this basically gives you indication what the magnitude as a function of position. For 3D, the expression looks identical except that you now have a z component, but more or less everything is still the same. All right, so you still need to understand how to take a magnitude. The magnitude in this case would be the square root of x squared plus y squared plus z squared. Okay, so next thing to do is to look at, well, can we basically look at various possible combinations of taking dot products between 2 different vectors, where one of the vectors is just that, a vector, and the other one is a differential vector. So if you look in the row here, you'll see TDS, NDS, TDS, NDS, N capital SDS, N capital SDS. So these are your differential vectors that you see here. Okay, so this is a differential length. Tangent to vectors is a differential length normal to the contour. This is a differential surface area. Differential length perpendicular to the contour. This is a differential surface area perpendicular to the surface. Same here. The only difference here is this is an open contour and this is a closed contour. This is an open contour. This is a closed contour. These would be 2D, 2D, and this is a surface in 3D. This is an open surface, whereas this would be a closed surface. Now we're going to give labels to each one of these things. If you see something like this, where you're going to integrate from an A and a B, we'll describe what all this is shortly. We're going to call this whole entity, which is a scalar, partial circulation. The textbook doesn't say it, and it has no physical meaning, but units-wise, it's still a circulation. Flux, on the other hand, doesn't matter. Flux basically can be over a small patch or over a closed surface. Right? So we can either basically, in this case, a closed contour. So this would be basically an open contour, just a small segment, and this basically would be over a closed contour. right? So we're going to define anything involving a normal to something, dot product with a field, as flux. This whole scalar is called flux. Now this will be the definition for circulation, where you go once around a loop. In fact, when you talk about a circulation, intuitively, you talk about going around the loop. So this is the actual definition for circulation. So this is flux on a closed contour. This is flux on an open surface, and this is flux on a closed surface. So like I said, anytime you see a dot product with a normal to something, it's by definition going to be called a flux. So this is 2D or 3D, 2D, 2D or 3D, 2D, only relevant for 3D. So here are now the different definitions. ds bold is the differential arc length, is the unit vector which is tangent to the contour times the magnitude of the arc length. Or it can also be written this way. This would be the differential surface area, a vector, which would be the unit vector that's normal to the surface times the magnitude of that differential surface area element. Also, this vector can be written like this. So this is basically ns would be the vector normal to the contour at a given position on the contour. Magnitude of differential arc length vector is this thing called ds. So now let's look at how these things typically might be used. So let's look at what we call geometrical outcomes and physical outcomes. Geometrical, where we're measuring things like area, length, and so on. So let's say we take this expression up here. We're going to be interested in more or less these four. So if I take f and let it be equal to t, okay, I'm just doing it for sake of argument, right? Then if I take this expression, substitute for f, I have the dot product between two unit vectors, so I'm just left with integrating from AB ds. What is that? That's just the length of a curved line between two points. If it's a closed contour, then this would basically be the total length or circumference, right, of the object or closed contour in question. Now the units of this, of course, would be meters. If you integrate ds, will be meters. You can also do it with the normal component. If I took f dot ns and let f be ns, the dot product between unit vectors would be 1. And you'd still end up more or less with exactly the same expression. Physically, what does it mean? It doesn't mean anything, but mathematically, it's perfectly okay to do so. Tangent vector makes more sense because you're moving in the same direction in which you're trying to measure length. In the case of the surface area, we can go through the same idea. So for instance here, if we let f be the normal to the surface, the unit vector, then the dot product between these normal vectors is 1, and you're just left with integrating over a surface. This would be over an open surface and be over a closed surface. And the units, of course, would be meters squared. So this would be for the 3D case. The circulation or partial circulation, either 2D or 3D. But when we're dealing with 2D and we're looking at flux, the flux formulation, or basically integrating, letting f be ns, then this can only apply in the 2D case. All right, let's look at it in terms of physical outputs. Let's say f represents something in particular. All right, so I've basically written out that f dot ds, this is a form of partial circulation, no physical meaning. This is circulation. And so if this is circulation, well, what are the units of f going to be? ds is units of length, right? So if the net result of this integration is circulation, then f will have to have units of circulation of circulation per meter. And this would apply in the 2D and the 3D case. On the other hand, flux, it's a little bit different. So for instance here, if we define this as being flux, as we said earlier, right, and this is length, then in 2D, flux would have units of flux per meter, flux density. So that's units of f, the flux density, be in terms of flux per meter. If you're dealing with a surface though, all right, so in this case, basically, this has units of meters squared, but this still has units of flux. That means that the flux density, F, will have units of flux per meter squared. Now, the moment you hear the word flux or circulation anywhere, it immediately refers to a vector property. If I just said density, like charge density, that's a scalar. But if I said charge flux density, whatever that would mean, that is a vector. Okay, so words are important here. All right, so physical outcomes. Let's see how these things could be used. So let's say F is lambda st, all right, and we're going to basically, in this case, call lambda a physical quantity, such as, for instance, something related to mass along a particular line. If I make this substitution, right, where mass depends on where you are on a curved line, then I end up with lambda s ds, okay? So this is over length, and this would be something of interest, like a mass. So the unit to this would be something divided by meter times the distance meter is the total mass over a curved line. So if it's kilograms, this number sign would be kilograms. If it's a closed contour, then instead of between 2 points, we typically use this curl sign here. This would be the total mass around the closed contour. Could be charge as well if you wanted. We could also do it using the formulation involving the normal to a contour, right? In which case you end up with exactly the same relationship. Although physically, this doesn't have any really meaning. The end result does, but why are we doing this? That's just the mathematics allows us to do it. And thirdly, then, was the case, for instance, if we're dealing with a mass on an area. So in this case, this sigma s here would be, for example, kilograms per meter squared. That's the amount of mass in occupying a small area. Well, if you make that substitution in for f, then we end up with sigma s ds. And so if you integrate, this is the total mass of some curved surface. This will be an open surface. This would be a closed surface. Okay, and so this more or less is when we're dealing with 3D objects. Okay, so this is just a summary in terms of, what's physical, what's not physical. And just nomenclature here, lambda of s is a short form, which says we're basically evaluating what the mass density is, or charge density, whatever the application, at every physical point along the curve, and every point basically on a 2D curve has an x and a y position. And for a 3D curve, then there'll be also a z position. On the other hand, if we're dealing with charge density, the only way you can define a surface is with two parameterization variables. So you would have a u and a v, for example. So in this case, for the 2D case, when you just have plane, this would just involve a mapping between x, y, and uv. But in a 3D case, which is an oriented surface, then there'll also be a z component. So depending where you are in 3D space, right, then there's a mapping between the points on the surface and the points basically referred to a flat plane. And this is something we'll be discussing much later when we talk about calculating things involving curved surfaces. All right, so again, this is just a rough repeat of what I had mentioned on the previous slide. Okay, so one other thing I'd like to mention is averages. Now that we're dealing with curved surfaces, curved lines, we're not restricting ourselves to planes anymore. Can we still use averages? The answer, of course, is yes. And so in this case, if I have a curved line and I want to, for instance, I want to find out what is the average mass along the curved line, then this F would be the mass density, which would have been something like lambda. And I integrate that over the length of the curve and divide it by the length of the curve. That's the average of this entity that you see here. So if this, like I said, this was a mass density, this would tell you what the average mass density is. Similarly, if you're dealing with a curved surface, then basically what you'd be looking at is something here which involves, say, kilograms per meter squared, and you're basically computing the total mass on the surface and dividing by the area of the surface. So this gives you basically the average mass density. You can also do with the volume as well. In this case, basically, this would be a volume density, and this would be an average volume density. Now, there are other things you can try. For instance, here, where it's a weighted average. This would represent the mass-weighted average position for a curved surface in 2D or 3D and volume, respectively. These are color-coded. So, friends, you have a curved line, and you're trying to figure out what is the balance point. If I basically took the curved line and put my finger at a certain point along it, at what point would it be balanced? And so that x average point would be more or less telling you where the balance point is. This is assuming, of course, that the gravitational field is constant, which generally is the case when we're dealing with terrestrial problems. The problem would have to be reformulated if the force varies as a function of position, or force field as a function of position. You can also do it for something which is a curved surface. So this would be the sort of the balance point for the x component. You can also do it for volume. This would be the x balance point in the case of a volume. Now, you can also basically do the same computation for the y and z component if necessary. If it's a two-dimensional object, then you'd also have an expression for y here. If it's a three-dimensional object, you would have expression for y and z as well. So there'll be an x average, a y average, and a z average. So these are things basically that we're not going to be looking at. The mathematics is straightforward. However, a more detailed discussion of this topic is given in chapter 16.6 of the textbook, which we will not cover, nor are you responsible for it. Well, that concludes lecture 17A. Thank you for listening.